So it's hybrid finite state machine. Now, another thing that I have obviously already noted over here that it's actually a timed hybrid finite state machine, because a finite state machine does not have access to a universal time. I made access to universal time. So where is the 6 p.m. stored? It's a global time that is always available. So here in an absolute sense, in a relative sense, I could have also said, so sometimes I make a reference to relative time. So I asked the peon who works to clean my table for exactly 10 minutes, and this is what the FSM of the peon will be after I've asked him to come. So it will be go to RK office. When he is at RK office, he listens to instructions. So the controller is listen to instructions. Instruction over. Then this is important, it's clean table. For how long? Exactly 10 minutes. So I can naively say after 10 minutes. So here I was making reference to absolute time, here I'm making reference to relative time. So that means every behavior, wherever the transition happens, there's a global timer and the timer is reset. That's like your vehicle. When you drive your vehicles, you've got the mile meter. The mile meter tells you how much have you driven in this trip, how much have you driven overall, and you can just make references to it. So as soon as I came here, the finite hybrid finite state machine, it knows that it needs to reset the timer. So a timer got reset, it's counting, 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 and I'm always checking for that timer. After 10 minutes, I basically say that my job is done, I am over, and therefore I will stop. If you want, then of course you can also send the peon back. So you can say go to, I'm not sure where do peons normally spend their time, but I think it's at the gate at this university. Gate reached, and then you stop. As of now, this is in it. So it's more correctly a timed hybrid finite state machine. Now it's a long notation, and therefore let me give it a short form. So I say that whatever graph I just drew, it's called as a behavioral finite state machine. Or it is the BFSM, where behavioral means both that it is timed and it's hybrid, and behavioral because our states are what? Our states are behavior. So I talked about this. So you say that based on some transition condition, you are changing from one behavior to the other behavior. Your behavior was go to G1, now your behavior is go to G2, then your behavior will be go to G3. So the term controller has been used as a behavior. Now, of course, it's more hybrid than that, because even the go to goal can be multiple hierarchies of behavior within themselves. But as of now, we're just referring to that as a simple behavior. So it's a behavior, and the overall thing is a finite state machine, and it's a generic graph. So there are libraries after libraries which will just take a BFSM as input, ask you to link all, write down all the transition conditions of the graph, write down all the behavior programs to be invoked when the transition happens, and then you just click on simulate, and they'll keep on checking the conditions and doing all the transitions that will happen. So that's a wonderful thing, that the labs become just writing down a graph. Most of them currently don't have a GUI, unfortunately, so the graphs need to be written as a XML. I personally hate it. There are people who have no problem writing graphs as XML. They have no option. So A nice complicated behavior. Just imagine programming this was just writing down this graph as an XML. How easy is that? Now what we'll do is that I'll take in probably another example in order to give you a sense of why is it not that easy. Now, I said over here, what really happens is that I'm doing a variety of things at the same time, and let's take in a very simple example. And my very simple example is that I want to meet my colleague who sits here, and after that, I want to just go and inspect the lab. And therefore, of course, what you will say, it's a very easy behavior. We'll make it easily. So you say init, no home, nothing. It's a new program that you just call, and all that needs to do is go to my colleague and go to lab and inspect lab. Once inspection is over, then you say stop. Very simple. So why did I write it? Now the problem is with this behavior over here. And the problem with this behavior over here is that unfortunately, my colleague these days sits at two places. One which is his normal place, right over here next to my office. That used to be my normal behavior. Okay, Rahul, come to my office. Yes, sir. I'll go That's all. Now the problem is he could be here or he could be over there taking his own classes, which is at the robotics classroom. And I do not know where he is. It's not that I cannot solve that problem. I can solve that problem. I first go to the lab. I first go to his normal place, and after I go to his normal place, if he's there, I do my talking. If he's not there, I go to the classroom. He will definitely be found over there. So, as a first example, what we have introduced is sensors. So, you have a schedule. However, the problem is that your immediate action is dependent on your sensors, what you see, and you'll only come to know when the robot is there. It doesn't know right now. Only when the robot goes there, it invokes its sensors, then it needs to decide what to do. So my colleague is at his usual venue, talk. He's not there at his usual venue, go to the classroom, talk. So let's try to model sensors in this simple behavior. So I again go init. This time I say go to his office. Okay. Now I need to make a decision. So I say action decider. You can give it a better name. So the two actions will be, of course, I'll talk, which is my usual action, or instead I may have to go to classroom. So I may have to go to classroom. And this is decided, of course, based on the sensor, and the sensor gives me the sensor reading value. So all that face recognition works, and the face recognition tells me what is the status. So I write down as reported by the sensor. If my colleague was at office, then I just straight away talk to him. On the other hand, if my colleague was not at office, then I have to go to the classroom. I can invoke the same sensor again, but then again, if he's not there in classroom, it becomes ambiguous. Where is he? I'm concerned about it. So let's assume that the colleague will be there at either of the two places he usually is. And therefore, I again talk to him. So it's classroom reached. And of course, thereafter, I can say talk over. So I go to lab. And at lab, I inspect. So I inspect lab, and of course, after inspection is done, inspection over, then I stop. Now, the only thing interesting is that there was one controller, a very primitive behavior. There was one very primitive behavior which is all the way up over here, and that's the one that invokes the sensor. So I could go this route or I could go this route. Which route do I go? It is entirely depend on what the sensor says. Let me take in another example. So my favorite example, I call the Pune, which I do call multiple times. We are Sarkari University, we are a government establishment, we only do paperwork. So we don't sign documents using smart writing devices like this. We still sign physical paper. So I call the Pune and the Pune comes over to me. So for the Pune, it's go to RK office. And once the Pune is at RK office, then I tell the Pune what to do. And usually it's one of the three things. So it's again action selector. Either I ask him to go to HOD office, or I ask the Pune to go to the director office. If you're wondering why, I have a academic profile for which I need to report every paper to HOD, which is all your stuff. I also have an unsettled profile, in which case I can report directly to the director. Or, of course, the third thing that I ask the Pune to do is to deliver some papers at the admin office. Let me not tell you the actual name of this office so as not to create problems and controversies. And then, of course, what really happens is after this Pune has given this thing, the Pune will just go to gate, and go to gate. So RK asks for HOD. So this is the sensor. RK asks for director, and RK asks for admin. So I'll tell. So if it was a robot, it will have microphone. This will be a HRI module for all the people who work in human-robot interaction. So this control behavior is the HRI, and that's what's a normal life of a peon. And of course, the peons, I love this job. So the normal job of a peon is to wait, which is also initially how they start off their day. They're just waiting. And in waiting, there's another sensor. So that's another sensor, and it says RK called. So I actually call up the peon, and the moment I call up the peon, the sensors respond, yes, sir, I'll be there. So this comes. So that's, of course, the image. And at 6 p.m. or over 6 p.m., the peon can stop working. So that's another one. So here I invoked in the sensors over here. This was sensor based. So which route does the peon follow? It depends upon the sensors. And this was a simple sensor. So the waiting behavior is also sensor based because the only transition condition is what is invoked by a sensor. So RK call, it goes around over here. So that's another interesting thing. Now imagine just that you had to simulate an office environment and you give this BFSM for one peon and he's going all the way, and then you got another BFSM for RK who based on some conditions is calling the peon. So there's a nice interaction between the two BFSMs. One releases a call and the other answers and comes to the call, and it's a great interaction between multi-agent system. Right now it's looking primitive because we're only modeling one BFSM for one agent, which is one peon, previously one RK, and that was interesting.